Welcome to the third day of this workshop. Our first speaker is Professor Suresh Nayak from ISI Bangalore. Suresh will be speaking on from cohomology to derived functors. Over to you, Suresh.
Okay, thank you. So actually, I must confess, I'm not going exactly as per what I had announced as titles. So I'm a bit behind. So even today, I may not be able to catch up, but hopefully by next lecture, I'll be at the right place. So continuing with our discussion earlier, I will sort of proceed in a similar style. So I'll have these pre-written notes and I will continue to scroll through them and talk about them. Okay, so last time we talked about mainly varieties, or what I called as algebraic sets. So I didn't want to impose one irreducibility condition on them. So that's why I just called them algebraic sets. And these were algebraic sets in affine space or projective space being places where we compactify, are sort of compact versions of the affine spaces. And we talked about how when one tries to construct, when one tries to look at nice functions, regular functions on these algebraic sets, over affine algebraic sets, we have plenty of them, but over non-affine ones, it's not so clear. And in fact, over projective algebraic sets, often one has very few of them. So for example, on projective space itself, only constant functions are the only ones which are regular. And in the complex analytic setup, that would amount to saying that the only holomorphic functions on CPN are, I mean, if you think of CPN as a complex manifold, then the only holomorphic functions on them are constants again. So global functions by themselves do not say anything about the underlying geometric object if you're dealing with the projective or in general quasi-projective varieties or algebraic sets. But if you're dealing with sufficiently local ones like affine ones, then they do then they actually do capture everything about it. So the affine coordinate ring actually contains all the. Okay, so where was I? I was saying that yeah. So therefore, we need to look at. Okay, so as I was saying. So we need a gadget which keeps track of the local data. And so we need to look at functions on all possible open sets. And that the gadget that does that is the notion of a sheaf. So we need to look at sheaves of regular functions. So regular functions on every open set of our algebraic set, algebraic variety or manifold. And if we do that, then we can hope to use that to actually extract geometric information, geometric invariants from our object. The geometric invariants that we have in mind are those motivated from complex geometry. So even though we put this pathological topology called the Zariski topology on the spaces, the actual topology that we have in mind for extracting geometric informations, especially from projective varieties or projective algebraic sets, is the complex one. So we look at that situation, and then based on that, we try to figure out how to extract that information from here. And we'll do that by setting up cohomological machinery. So today's lecture will also be more of sort of a foundational kind of thing. And hopefully I'll be up to coming to the duality kind of results by next lecture. Okay, so let's start with let's see, X a topological space. And so I'll recall some definitions again for those who are studying algebraic geometry or who are who have already studied it. This might be a bit repetitive. I apologize for that, but I hope those who are not studying algebraic geometry or who are looking in other subjects benefit out of it. So here it is. X is a topological space, pre-abelian groups, as we talked about yesterday, is simply a functorial assignment from every open set. You assign to every open set, you assign an abelian group, and it's functorial in the sense that when you go to a smaller open set, you have a group homomorphism from f of u to f of v, where v is a smaller open set. Such a pre-sheaf is additionally, if it satisfies an additional gluing condition, it's called a sheaf. So a sheaf of abelian groups is nothing but a pre-sheaf which has a gluing condition that if for any open set, if I cover it by if I have an open cover VI, then this gluing condition holds that we saw yesterday. So I won't elaborate too much on it, except that saying that every section or every element of f of u is uniquely determined by the condition that it consists of one element of f of vi over that open cover, which agree on the pairwise intersection. That's what this exactness of the sequence is. So a sheaf of rings is nothing but a sheaf of abelian groups together with a multiplicative structure, and this the restriction maps they all respect the multiplication. One goes to one and all those things. So that's a sheaf of rings on X. Sheaf of rings are going to be important because that will be our those will be our ring of regular functions and other possible examples. So a map of sheaves or map of pre-sheaves. So pre-sheaves is a larger category than sheaves. These are sheaves are pre-sheaves which satisfy a gluing condition. So typically when I define something for pre-sheaf, of course, it's immediately also defined for sheaves. Map of pre-sheaves is just, again, it's a functorial definition. So given f to g, I mean, to give a map from f to a sheaf on X to a g, another sheaf g on X means to supply for every open set group homomorphism like this. And moreover, if it's compatible with the restriction homomorphism. So if you have a open set V and you have these restriction maps, then these group homomorphisms you'll specify on U and on V, they are compatible like this. Okay, given a pre-sheaf on X, so also, for example, given a sheaf on X, so for any point on the on X, we can define its stock at X, and that is simply the direct limit of f of u as you shrink your open sets. You look at all open neighborhoods of X. So you shrink those open sets U around X, and as you shrink them, you get a directed set of open neighborhoods of X, and you look at the corresponding directed sequence of group homomorphisms and take their direct limit. So that direct limit is the stock. So this is a group at, I mean, there is a group associated to each point X, and as we will see, if it's if F was a sheaf of rings, this will be often, I mean, this will of course be a ring, but it will also be quite often a local ring. So we'll come to that. So if F is a pre-sheaf on X, then one can actually sheafify it. So we won't really, I mean, this thing is quite important, but we won't really emphasize it right now. So just say that given a pre-sheaf, the sheafification has a universal property that any map from the pre-sheaf to a sheaf G uniquely factors through it. And the way it is basically made up is you look at sections of you for any open set U, you assign you look at all open covers of U, and over that open covers you look at various sections which agree on overlaps. So since it's only a pre-sheaf, these such a gluing data may not give rise to a section on F, but you look at such collections and you put a obvious equivalence class on them, and then you say that such equivalence classes of data actually gives you a section over an open set U, and that is how you look at the associated pre-sheaf. So so that's your associated pre-sheaf, and then you have so the basic property is that for any point in X, I have isomorphism of stocks, fx to f. I mean, the sheafification is denoted as f plus, and so fx and f plus x have the same stock. So in some sense, truly locally, nothing much is happening if you start concentrating very close to the point little x. But in some sense, it's the, I mean, it's in the limiting situation. So over open sets, however, you will have a difference. So f plus may have more or less sections. So there may be some quotienting and there may be some increasing of the corresponding section. So that's all I will say about it. So essentially, we use this sheafification process all the time implicitly. So so a sequence of maps like this between pre-sheaves is called exact if for all points in X, the corresponding map of stocks. So if I give you a map F to G, it's easy to see that you'll get a map, induced map of stocks. So that'll be the map Fx to Gx. And if this is exact, then we'll say that this sequence is exact. So exactness is checked in some sense pointwise like this by taking stocks. One should keep in mind that so immediately this gives rise to an abelian category structure on the set of all sheaves. I forgot to say that. And in particular, for example, you can have a inclusion of sheaves like this, which is just inclusion, which is equivalent to saying there's an inclusion. In fact, it's if and only if inclusion of pre-sheaves. So for every open set f of u and g of u are there's an inclusion. However, one can also, since it's an abelian category and exactness can be defined like this, one can talk about surjective map of sheaves, but it turns out that such a surjective definition or the notion of a surjective map does not really translate into being surjective at the level of sections on every open set. And we'll come to some interesting examples below. So just wait for a while and we'll come to that. So what one can therefore do is now for any sheaf F, one can assign to it its sections over an open set. So the sections means, okay, sections functor is another name for just F of U. So that's the assignment that we had in the definition of sheaf. For every U, we were assigning an abelian group. So that abelian group is called the group of sections over U of script F. And one can make a functor out of it because we can have an exact sequence of sheaves or pre-sheaves like this, and we can apply this functor. So that will give rise to a sequence like this. And it turns out, so I will not prove this, but it's not difficult to see that if you have an exact sequence like this, what one gets is an exact sequence like this. Notice what is missing is the exactness on the right. So it's only exact on the left. So the sections functor is only exact on the left. Again, these examples which we see below will highlight this. And in fact, this is the sort of the main reason for cohomology theories in algebraic geometry. Most of them arise from the fact that this sections functor is not exact always. And so the fact that this is not exact is another way of saying that this quotient, this last sheaf H, its sections over the open set U are not exactly FU over GU over FU. So it might be something more. And so in fact, the sheaf H is not equal to the pre-sheaf G divided by the pre-sheaf F. I mean, F and G and H are all sheaves. Here, I forgot to say that. So let me just say that these are sheaves. Okay, and so these are all sheaves here, and this is an exact sequence of sheaves. But you think of, you look at G over H, F as a quotient of pre-sheaves, and then you sheafify it, and that will give you H, and that is what the exactness really means. So there's a sheafification involved here, and that is the obstruction to, I mean, that's the reason why it's not exact on the right here. So this is some basics of sheaf theory. And now what happens if you change the topological space? So you go from one topological space to another one, take a continuous map. Then a sheaf on X gives rise to a sheaf on Y. So for example, if you have a sheaf on X, you can look at F lower star F, which is defined as follows. Take an open set V here, look at its inverse image. And on that inverse image, I can associate a group because I already have a sheaf here. So look at F of the inverse image. So doing this for various open sets here gives rise to an assignment. V goes to some abelian group. And therefore, that gives rise to, then one checks easily that that gives rise to a sheaf on X. So sorry, sheaf on Y. So given a sheaf here, I have obtained a sheaf here. And I can try to go the reverse way. I mean, I shouldn't call it reverse, but I can try to go in the other direction. So start with a sheaf on Y, call it G, and then I can try to construct a sheaf on X. And so this is how one does it. So it's called F inverse G. So now the situation is complicated because I have a sheaf given here, and now for every open set, I need to do something. But for an open set here, its image here is no longer, I mean, I don't have a natural way of assigning an open set here, looking at an open set here. So what we do is we look at all those open sets which contain the image of the open set here. So if the open set is U, I look at F of U and look at all V which contains F of U, or you can say U is inside F inverse V. And then I look at the G of V for this, and I try to, in some sense, pick the smallest one. So there may not be any smallest one. So I take the direct limit over all such GV. So that is like trying to take the smallest V which contains the image of U. And so that's a substitute for that. And when I do that, I'll get a nice pre-sheaf that will immediately follow from the definitions. I have to sheafify it to make it into a sheaf. So that sheaf is called F inverse G. Sheaves are more important than pre-sheaves. Pre-sheaves are easier to construct, but all one has to do is then sheafify things, and then that will give us sheaves. And that's more important because in some sense that is trying to capture local data, things which are obtained by gluing stuff over a small, an open cover. So one has to always sheafify, and that is kind of the important thing. So here are two examples which illustrate this process. So for example, if y is a point, then you're mapping x to a point, and then what is lower star? So the point has nothing there, so its inverse image is the whole space. So you'll be assigning to that particular point the f of the whole space. So it will turn out to be therefore the global sections functor, the sections over all of x. On the other hand, if I do F inverse, where y is now a point, then over a point, there is hardly any there's hardly any sheaf to assign. Basically, there's just one open set. So might as well call it an abelian group. So look at an abelian group A, and then F inverse of this abelian group is basically for every open set, you'll be trying to assign A. That's what it means. So that's why we'll call it constant. But if you assign to every open set the group A, you will actually not get a sheaf. You'll only get a pre-sheaf, so you have to sheafify it. So that's why I put a apostrophe there, exclamation mark. Sorry, what is it? Quotation marks there. So it's actually the sheafification of the constant pre-sheaf, and it's still called a constant sheaf. So this is a constant sheaf, which is basically on connected open sets. I am just assigning the group A. But when the open set has more components, then I'll be looking at functions which are constant on each connected component. Okay, and again, these definitions, they simplify considerably if instead of y being a point, if you take x being a point. So if x is a point, we will see that you are assigning, so for example, if you take a sheaf G here, and if you have a point here, then this point has an image. So call that little y, and then you can easily go through a definition and see that F inverse G is nothing but the stock at Gy. And on the other hand, if you start with a sheaf on the left-hand side, but it's just a point now, so then what you will get is F lower star of that so it's just a point. So on that point, you can only put a single abelian group. So F lower star of that abelian group will be turn out to be a sheaf on Y, which is constant on the closure of Y. So basic properties of F lower star and F inverse are that F lower star is left exact. This is sort of consistent with the fact that, no, in fact, we saw F lower star. In fact, global sections functor is also like F lower star. It's a special case of F lower star we said here. So F lower star in general is left exact. F inverse is always exact. And in fact, they are adjoint functors. And that's what I wanted to say here. So F lower star is a left exact sort of also follows from the fact that it's a right adjoint here. So these are elementary properties. They need a little bit of proof, but we'll not go through that. So these are the basic properties. So here are some interesting examples you should keep in mind. So first example is, so take a complex manifold, or in fact, for simplicity, I'll just take a Riemann surface. And on that Riemann surface, I have these sheaves here. So this is the constant sheaf. So that means on every open set, on every connected open set, I have just constant functions. And on connected components, I may have the functions may vary, the values may vary. This is the sheaf of holomorphic functions. So every open set, I'll simply look at holomorphic functions from U to C. And this is holomorphic functions which are nowhere vanishing. So holomorphic functions from U to C star. And this map is the exponentiation map here, e to the power 2 pi I f. Then one can easily see that this is this. Oh, oops, there was a 0 here. So one can easily see that this is in fact an exact sequence of sheaves. And for that, what one has to do is one has to, and okay, I'll come to that. Yeah, so what one has to do is one has to check that over sufficiently small open sets. So to check exactness, you have to check exactness at the level of stocks. And it turns out that if you check over sufficiently small open sets, given a section here, you can somehow find a section here that itself will imply that it's surjective. And this you can do because over sufficiently small open sets, you can assume are simply connected. And if they are simply connected, you can take a natural log of your function. And so you can do that, but globally that may not be true. And so this is globally the exactness fails here unless X is simply connected. So because you may have a function here which may not admit a natural log. So this is one example of sheaves which are sort of carrying locally defined data, but you have an exact sequence. But when you apply the global sections functor, you are really trying to capture something, a global property, and the failure to be exact will depend on global properties of X. Here's another, here are two more examples. So for example, X is a C infinity manifold, and you can simply, so you can look at this, what is called as a DRAM complex of it, but this is the local DRAM complex. So this is the complex of sheaves. So on every open set, you look at one forms, two forms, so C infinity, one forms, two forms, and so on and so forth. So then the standard Poincaré lemma will tell you that this is actually exact sequence, and so therefore, if you drop the R term here and throw in a 0 here straight away, then this is in fact omega 0, and that is the complex omega dot. And if you apply the global sections of that, you get the DRAM groups, and you get the DRAM complex, the global DRAM complex of X, and the homology of that is a DRAM cohomology. DRAM cohomology. So therefore, once again, we have a sequence of sheaves which is exact, but that doesn't really translate into applying. If you apply the global sections functor, that doesn't really translate into getting an exact complex. And the homology of that complex carries vital information about the manifold. Similar example is that of coming from topology. So locally contractible topological space, so that again, this complex is exact, and take a ring A and look at singular cochains defined over A. So for every open set, you put singular cochains defined over A, and you get this singular cochain complex. And so sorry, if you're doing it for every open set, you'll get a pre-sheaf of, you'll get a sequence of pre-sheaves. And in fact, you should sheafify them, so they are not really guaranteed to be sheaves. So you sheafify them, and then what you get is an exact sequence like this. Exactness follows from the local contractibility property again, because for locally contractible spaces, we know that this singular cochain complex is exact. So locally, this is exact over small open sets, and that will tell you that this is an exact sequence of sheaves. But if you look at its global sections, of course, again, without the A term here, global sections of the C dot complex, then what you're measuring is the singular cohomology. So again, this highlights the fact that quite important topological properties of the space are being captured by looking at exact sequence of sheaves and applying the global sections functor. Okay, so in the context of algebraic geometry, our objects will not be manifolds or topological spaces, but instead they will be what are called as schemes. So these are generalization of varieties, algebraic varieties or algebraic sets. So here's a quick summary of their definitions. So an affine scheme is modeled on affine varieties or affine algebraic sets. So in an affine algebraic set, the coordinate ring is important. And in the coordinate ring, from the coordinate ring, I can recover the entire affine algebraic set by looking at its maximal ideals. So this is what I do for an arbitrary ring, and this is what we need to do if we want to work over non-algebraically closed fields or arithmetic situation or more general situation. So start with the ring A and look at what is called as the prime spectrum of A. This is a set of all prime ideals in A. And again, just like algebraic sets or algebraic varieties, put the Zariski topology on them. So earlier we would say, okay, look at the set of all functions vanishing on a given, given an ideal I, no mind. So given an ideal I, look at the zero locus of that. So the algebraic way of looking at the zero locus is to look at, which would amount to saying in the classical case, look at all maximal ideals, because maximal ideals are the points which contain I. So now I would look at all prime ideals. And I'll declare those to be the closed sets. This defines Zariski topology on my spectrum, the prime spectrum. So certain collections of primes are closed sets. It's hard to get used to this if you are seeing it for the first time. So just pretend that this will be very analogous to what we have for algebraic, the basic objects in algebraic geometry, like algebraic varieties, algebraic sets, quasi-affine, projective, all those things. So the complement of one equation is typically gives you a basis of neighborhoods. So that is my notation for that. XF, X minus ZF. These are in some sense, you can think of them as the smallest open sets because their complements are in some sense the largest closed sets. And to that we assign the ring AF, with F inverted. So if we do that, then it somehow uniquely gives rise to a sheaf of rings on X, which we'll call it as OX. So this is just like we said in the previous lecture. So X together with this sheaf of rings is called an affine scheme. So this is our substitute for an affine algebraic set, like a parabola or a hyperboloid. So this is our substitute for that, a more abstract way of looking at things. And we'll write it as spectrum A. And what we have done is, instead of having just maximal ideals in the algebraically closed case, we have also introduced prime ideals. So that complicates things a little bit, but in fact, it turns out to be useful. A basic technical fact is that the local rings will turn out to be of OX will turn out to be local. Sorry, I mean, it will turn out to be a local ring. Okay. And the stocks will turn out to be local rings. That's what I meant. And if keep in mind that if K is a field, then there are no ideals in K. Just 0 is the only ideal. So spec K is just one point, which is the point, the prime ideal 0. So that would seem to suggest that different spectrum of different fields are all same in some sense, but that's only topologically. And that's because our basic definition involves two things. You have to put a topology and you have to put a ring, sheaf of rings. So in the case of a field, I'll be putting just a point here because just the 0 ideal, but I'll also be putting the ring here, and that will distinguish between the spectrum of different fields. So spectrum of any field is a point, but there's also a ring sitting there, and this is important to keep in mind. A scheme is just obtained, just like we did last time, is obtained by gluing together various affine schemes. So simply glue them together and you get a scheme here. So X is equal to union of UI, and then a scheme is a topological space with a sheaf of rings, such that when you restrict to UI, this topological space with a sheaf of rings is isomorphic to the Sorry, I again lost my internet connection, and now I'm back. And again, I have to share my screen. So let's see. There we go. Is it visible now? Can you hear me?
Yes.
Ah, okay, thanks. Okay, sorry about that. So somehow my internet connection seems to be flaky today. Okay, so where was I? Okay, so I have a continuous function. Yeah, so a morphism of schemes is just, again, it's somewhat similar to what we had yesterday, how we defined a regular map. So it's a continuous function, which gives us a way of, I mean, then you have this, let's see, so you have this, I mean, given a function here, basically given a regular function here, you want to pull it back, and that pullback should also be regular here. That is somehow the idea. So given a regular function f here on some open set, it should give rise to regular function here. So that is what this map will do. It will map it, it will send it to some regular function here. So that is, okay, anyway, this is another one of those technical definitions. So this is what finally what it comes down to. Okay, let's get by this. And here are some basic constructions. So given a scheme X and given F and G, two OX modules, tensor product you can define by simply taking the tensor product over open sets over all the open sets, and then assigning that to the open set U. And that may not be a sheaf, it will only be a pre-sheaf, and then you just sheafify it. So that is your tensor product F tensor G. So again, this construction looks pretty complicated because first you do tensor, then you do sheafify. So we essentially use only the basic defining property, and that turns out to be enough. The universal property of sheaves is all we need most of the time. So to eliminate this multi-step process, or to ignore the multi-step process here. And similarly, HOM, so given two sheaves F and G, one can make a new sheaf out of them, HOM, which is, it's called a local HOM. So just look at all the sheaf homomorphisms from F restricted to U to G restricted to U. And these are homomorphisms which respect the scalars. So it's OX linear homomorphisms, or OX restricted to U linear homomorphisms from F to G. And if you do this for every U, then it'll automatically, this will turn out to be a sheaf. So you don't have to sheafify it. That's your sheaf HOM. And a morphism between two schemes will always give rise to, so given a morphism between two schemes and given a sheaf G here, or a scheme, not just sheaf, this is actually an OY module, you can pull it back, and that's called F upper star G. So we already had one operation F inverse G, so given a sheaf G, one can pull it back, but that may not pick up an OX module structure. So therefore, you have to do this. You have to, I mean, it will automatically have an F inverse OY module structure. This is a smaller sheaf of rings on X, and then I shouldn't say smaller, whatever. In fact, if at all, it's bigger. So hang on. Yeah, no, yeah, I should call it smaller. Okay, in some vague sense. So, and then over this, OX is the thing which it's mapping to. So we just tensor it with that. Again, it satisfies a certain adjointness here, which we will probably use it later. In the category of schemes, fiber products exist, and they are basically, the local picture is as follows. So if you replace X, Y, Z by affine varieties, then X is spec B, Y is spec C, and this is spec A. So these are spectrums of rings. And over the category of rings, the maps are in the opposite directions. So if you have a map of schemes spec B to spec A, that means you have a map of rings from A to B. And you have a map of rings from A to C, because the map of functions always goes in the opposite direction. So I have A to B like this, A to C like this. And then the fiber product just turns out to be the universal property of tensor product. So therefore, you just put the spectrum of the tensor product here. That will be your fiber product. And it will have all the right properties. So for example, in particular, if I have a polynomial ring, spec R x1 to xn, then I can think of it as coming from a polynomial ring over K by tensor product. And so therefore, this is affine space over R. I'll call it affine space over R. So this, I can think of it as taking spec R and tensoring with the affine space over K. I'm taking the fiber product. So this is a mistake here. This should be fiber product here. Okay. Finally, an important construction is that of the projective spectrum. It's similar to the affine spectrum, except we keep track of homogeneous stuff. So this is what we saw for projective varieties. So here's your graded ring. And instead of looking at all prime ideals, you only look at homogeneous prime ideals. So those will correspond to somehow lines in your affine AN+1. That's what we did last time. Zariski topology, instead of looking at arbitrary ideal, you look at only homogeneous ideal and look at all. So look at all homogeneous primes. So there's one small extra condition here, that the homogeneous prime should not be too big. So it should not contain all of A1 to A infinity, all of them. So so you look at all primes, homogeneous primes, which contain the ideal I, and declare them to be a closed sets. One can check that this forms a topology. That's the Zariski topology on projective spectrum. And one has similarly, one can talk about basic open sets. And it turns out these basic open sets are affine, in fact, just like we had for projective varieties. And you can assign to them a nice ring here. And this ring is, again, you invert F and then look at the degree 0 part. It's like taking ratios of homogeneous polynomials where the denominator is some power of F. Which have the same degree. I mean, that's what we were doing when we were looking at the functions on projective spaces. We had to look at ratios of homogeneous polynomials of same degree. So that amounts to looking at degree 0 fractions. So this is the degree 0 fractions in this, and that is your AF. This again gives rise to a sheaf of rings, which locally is actually, over these open sets, it will turn out to be simply affine. These will turn out to be affine schemes. So these are your affine schemes, and this is scheme here. So for example, if so this is the construction that we saw last time. You take a field and you take n plus 1 variables, and you look at all the prime homogeneous prime ideals there, and look at the Zariski topology and so on and so forth. So if you do that, then you get projective space over the field. So instead, you can do it over any ring, and you get projective space over the ring, and then that's obtained by, again, fiber product with over a field or over spec Z, because Z is inside any ring, or Z maps to any ring. So you can also talk about that. Well, sort of a useful thing is, most of the rings that come in geometry, or schemes that arise in geometry, have this extra property called Noetherianness, which is kind of convenient. So it says that you can cover it by finitely many affine opens. So that is what this compact means. Compact is actually Zariski compact, so it's not really compact in the usual sense, because these are not housed-off spaces typically. The Zariski topology is usually a pathological topology. It's a bookkeeping device. And so it's compact in that sense. So it's covered by finitely many affine opens, and on each affine open, it's coming from a Noetherian ring. So all ideals are finitely generated, etc. Okay, let's talk about modules. So modules on uh, ringed space, sorry, on scheme. So again, we'll first do the local picture. Local picture is affine scheme. So it's the spectrum, prime spectrum of a ring A. Here, if I give you an A module, then we can look at M tilde, and it's defined as follows. On basic affine open sets, you look at MF. So on basic affine open sets, the corresponding ring, there's a sheaf of rings here, and the corresponding ring is AF, and the corresponding module I assign is MF. So what I'll get is a sheaf of, I'll get an OX module here. So this is M tilde is an OX module. If M was A, then I'm just looking at OX. And if M is something else, then you can just make it out of OX. So write down a presentation of M, or yeah, you write down a presentation of M, you can get a presentation in terms of OX. I forgot to mention here, but the global sections of M tilde is again M. So maybe it's worth writing here. Global sections of M tilde is M. This is important. So it says that you really don't get anything new by, so this is always the case over all these affine objects. You don't really get anything new by constructing a local object like this. You still got back only M, nothing more. Its talk is at any point P is MP, and this is an exact functor. These are all easy to see. So now we come to the definition of coherent and quasi-coherent modules. So for simplicity, I'll restrict myself to Noetherian schemes. Otherwise, it's a slightly more elaborate definition. So an OX module F is called quasi-coherent if so Noetherian scheme is covered by finitely many affine opens. So cover it by such one, take one such cover, and on that cover, if you restrict your sheaf, it should look like M tilde for that A module M, for some A module M. So then we call it quasi-coherent. If it's finitely generated, then we'll call it coherent. So that's the difference between coherent and quasi-coherent. So one situation where these things arise is in the case of projective spectrum. So take a graded ring, n graded again means the ring is sitting in positive degrees. And for simplicity, we will assume, otherwise there are more technical hurdles, technical complications that might arise at some later stage. So we'll assume that it's generated by the degree 1 terms here. So there are no funny higher degree terms needed to generate it. Everything is generated by degree 1. So all degree 2 are simply quadratic expressions in degree 1, and so on and so forth. So we'll assume that that is the typical situation that one initially encounters when one does projective geometry. So this is really fairly general, so it's not such a restrictive hypothesis. And take the projective spectrum of A and let M be a graded A module. So again, M will also admit a grading like this. I may sometimes even allow negative degrees, so that's okay. In fact, we will soon allow some negative degrees also. So then one can again, on basic affine open sets like this, XF, one looks at degree 0 fractions in the localization of M, because one is dealing with homogeneous things. So you don't do the same thing that you would do over an affine thing. You have to look at homogeneous fraction, degree 0 fractions when you look at fractions. And this gives rise to a module which will again, for some reason, it's called M tilde, because in fact it does look like M tilde on these basic. It does look like tilde of something on these basic affine open sets. So it will turn out this is also quasi-coherent, and if it is finitely generated, then in fact it is coherent. Here's a interesting situation which doesn't arise in the affine case, and this is peculiar to the projective situation only. So because you have a grading, you look at the module A1. So this is an important construction. So A of 1 is just shift. Okay, sorry. This is shift A to the left as a graded module by one place. So that means that M of D is A of D plus 1. So we write, so if you do that, then you can, you get a new graded module, which pretty much looks like A. All we have done is taken this and just shifted it one place to the left. Everything has gone one place to the left. So it looks pretty much like A, but in fact, since we are looking at, I mean, over basic affines, we will be looking at degree zero fractions. Some things will change because now degree zero fractions will have a different meaning because degree itself has changed of each term. So you'll get something slightly different. This module is denoted as OX1 because you have shifted by one place to the left. And in general, if you shift D places to the left where D is positive or negative integers, so if D is negative, it means it's actually you're shifting to the right. So if you shift D places to the left, you call it OX of D. So what is easy to see is that over affine patches, this is in fact just looking not very different from OX itself. So OX of D over sufficiently small open sets, in fact over these open sets, is isomorphic to OX itself. So therefore it will turn out to be a locally free sheaf of rank 1. So it's what is sometimes called invertible sheaf, and by abuse of notation terminology is also called as a line bundle. So this is a locally free sheaf of rank 1. Here are some basic properties. So to cut down on time because I lost some time in my power outages. So let me just say here, okay, but this is an important example, so might as well say something here. So this is a polynomial ring here, and I mean, that's what I took. I started with a graded ring. So now let's specifically take a polynomial ring. Then OX of D, it will turn out its global sections are spanned by degree D monomials in x1 to xn plus 1. And that really follows from the fact that, I mean, you have to, okay, no, I mean, you really have to do some local calculations and see that you can glue things together. Essentially, it comes from the fact that when you shift everything to the left, see, originally A naught had only the field K sitting there, and those give rise to constant functions, and those were your only globally available functions. But now if you shift everything to the left, then suddenly A1 comes here, and you do pick up degree zero fractions with just one in the denominator, which has all these linear terms in them, because now everything has become degree zero by definition. That's the definition of A of 1. And so therefore, so you will get degree 1 terms if you shift by 1, you will get all the linear monomials in Xis, and so on and so forth. So if you shift by D, you will get degree D monomials. And so that tells you that OX of M should not be isomorphic to OX of N for M not equal to N, but actually it shows only for positive M and N, but then you can sort of dualize it. So these calculations here tell you that if you dualize them, then in fact, dual means that just look at HOM OXD into OX. So if you do HOM OXD into OX, that's called the dual, and that will be OX of minus D. And so therefore, by doing that, we can see that in fact, for all M and N, OXM is not isomorphic to OXN. So this is an interesting class of line bundles on or invertible sheaves on X. But here's another interesting class which one cannot ignore in geometry, and that's basically the tangent and the cotangent bundles that you would like to define on a manifold. So in algebraic geometry, it turns out it's easier to talk about cotangent modules. Somehow there's a technical point, but it's much easier. It's very naturally available, and one can define it in vast generality. So cotangent modules are easily available. So when I have a map x to y of, if you can think of varieties or algebraic sets in affine or projective space, or more generally, you have a morphism of schemes, one can define the relative cotangent module, or what is called as relative differential one forms. So these are basically, if you think of, the corresponding dual of this, in the context of manifolds, would be the relative tangents. So those are basically the kernels of, that will be made up. If this was a submersion, then if you look at a map of tangent spaces, there'll be a kernel here, and those kernels will give rise to relative tangent spaces, and you put them up together, that will form some kind of a bundle here, and that will be your relative tangent bundle, and this is the dual of that. So that is what one would do in the case of manifolds, but in the case of algebraic geometry, in fact, this is much easier to define, and one gets it pretty easily. So that is called the relative cotangent module. I won't go through the definition, but suffices to say that if you have, say, a polynomial ring, then over spec R is nothing but a free module with basis dx1 to dxn. And of course, it's a quasi-coherent, it's a coherent module on X, and so you have to make a tilde out of it. So this will be your, I'm thinking of omega1 as a sheaf here. So the same notation omega1 can be used for the module as an R module, but you apply tilde to it and you get the corresponding sheaf. So we'll typically use the same kind of notation for both the modules and the sheaves. And an important usage or important sort of, okay, I shouldn't say, well, yeah, usage is the notion of smooth morphisms. So a smooth morphism in so smooth morphism between two manifold schemes. So I won't go through a definition, but it's almost, with some minor conditions here, is equivalent to saying that omega1 x over y is locally free of rank n. In fact, certainly it implies that, and one can say that. So what is smooth or non-singular? Okay, that's kind of it's some sort of a Jacobian condition. It says that okay, pretend, for example, if y is little k, then it says that this is actually looking like a manifold. It doesn't have any singularity. And that amounts to saying that if you take a small piece of it and embed it in your complex space, then it's actually a regular submanifold. So, or yeah, it's something like that. So I'm just giving you an intuitive idea. So exact technical definition is, we'll not get into that. Again, one can define it in terms of equations and polynomials and Jacobian conditions. So the thing that comes out is that if it is non-singular or smooth, then omega1 is locally free of rank n, and that n is then the relative dimension between x and y. So let me now come towards the, so there's not much remaining, but I think I have more or less short my time, but can I take a few more minutes because there were a couple of interruptions?
Yeah, sure, Suresh.
Yeah.
I think there's a comment in the chat box. Can you see your chat box? Or
No.
if Manoj wants to unmute himself and say something.
Just on the slide slightly above this, I think it should be a free module over the polynomial ring, not over R.
Okay. Sorry. Yeah, thank you.
Not the space, the one.
Yeah, I understand. This is a free module over this polynomial ring. Correct. Thank you. Yeah. So that is this is free module, not Rn. So free, correct. So this is okay. So let's call this as, okay. Let's make it P, and where P is equal to R x1 to xn. Thanks. Okay. All right. So this is the module of differentials on for a smooth map, relative cotangent module. So for example, you can always think of y as a point. So it is spectrum of k, and then x is some nice variety over k, nice algebraic projective or affine algebraic variety over k. And then one is talking about the usual non-singular. What in complex algebraic situation would give you a complex manifold. So the important thing about, so now we come to an important calculation. So suppose I'm looking at projective space P and K. The Euler exact sequence on P and K allows you to say something about the module of differentials on P and K. So for simplicity, I mean, just for the generality, instead of K is a field, I think okay, I've seen to have written, and that it will work anyway. So let A be a ring instead, and take, okay, oops. So this is again, sorry, I think I was in a bit of a hurry towards the end. So x n plus 1. So this is the homogeneous coordinate ring for your projective space. And I will be looking at proj of R. So that is my PNA. And so if you want, you can think of A as a field. So this is the field, complex numbers if you like, and this is homogeneous coordinate ring over that. And what we are saying is that the module of differentials of this projective space, which is the left term here, has the following. So now it is appearing in this form. So it is not a presentation of that, but instead, so in fact, it's a tangent space, a tangent bundle, which has the presentation. So in fact, at the level of tangents, you can interpret this nicely. But anyway, let me first explain this exact sequence. So this goes into this OX minus 1. Remember, this is the -1 twisting that we did here, right here. So this is the shift here, but you shift it by one place to the right. So you shift that one place to the right, and that is what is involved here. And then take n plus 1 copies of that and take the direct sum. So this is a direct sum of, so this is actually not, so individually this is a line bundle, and you take direct sum of n plus 1 of them. So you get a locally free sheaf of rank n plus 1. So vector bundle if you like. And then there's this has a co-kernel OX here. So in fact, there are nice intuitive explanations for these maps here. So for example, you can say that this map is really resulting from simply the universal, from the derivation from A to, from R to omega tilde, sorry, omega of R over A. Omega of R over A has n plus 1, I mean, it's spanned by dx1 to dxn plus 1. And so that derivation is what is giving rise to this. But you see that omega R over A is actually defined not over the projective spectrum, but defined over the affine spectrum, AN plus 1. And so in some sense, to understand the sequence, you have to really go into this covering. I mean, in some sense, you have to go here, AN plus 1 minus 0 to PN. I mean, in some sense, this is what is really happening. And if you look at this is, you can think of this as vibration with fibers K star, C star, or K star over each point. And so therefore, the corresponding tangent spaces will, so this is your tangent bundle, so to speak, on this affine cone. And that's why you have n plus 1 copies here. This is your, I mean, I'm dualizing now. So this is my tangent space here, tangent bundle of omega 1 here. And then this is corresponding to the tangent space of the fiber. So that in the reverse direction, if you dualize it, then you get a map exact sequence in the reverse direction. That is the intuition to understand. I mean, but of course, if you want to justify this over A and so on and so forth, you have to do some local calculations and check it. You can see it in Hartshorne's textbook. It's all done there. So it's not really hard to prove this. And once you prove this, out of this comes a nice fact that omega n x over y, that's a relative cotangent. This is the nth exterior power of the relative cotangent module. So I'm just taking the determinant of this exact sequence. So if I take, these are all locally free sheaves. So I take, means I take the exterior power of the highest order of each one of them. Then the highest exterior power of this is rank n module. So therefore the highest exterior power is this one here. And that tensor with highest exterior power, which is 1 here, but that's trivial because this is OX, so that itself is isomorphic to the highest exterior power here, which is n plus 1th exterior power. So that is what I've written here. And that one can show because these are all invertible line bundles. So it's just tensor product of these guys. So that's just OX minus n minus 1. So this is the important fact. And this is what we will use in the next lecture. That omega n of the relative projective space is always, so the nth exterior power is simply an invertible sheaf. So omega 1 is rank n, and this is rank 1 because I've taken the nth exterior power. And this rank 1 module is simply O shifted by minus n minus 1. It has no global sections, but this shift, we will keep track of it. Okay, so I think I can end my lectures here. Let me see. Okay, I have just written this much. So let me just say this and we'll stop here. So the last thing is that I'm interested in cohomology of computing cohomology of various modules. So this is what we will be doing in algebraic geometry, and our duality statements will be phrased in those terms. So to do that, to define cohomology, one needs the notion of injectives, which we all know. But one should say that it's also available in all these other categories that one is working with. So for example, if you're working with the category of modules over a scheme X, or more generally X is a topological space and OX is a sheaf of rings, then this is an abelian category of OX modules, and inside that there are enough injectives. So for example, given an OX module F, what you do is you embed it inside a direct product of things like this. So what are these things? Go to each point and embed it inside an OXX. So this is a ring, and now just do an honest, just find an injective module containing this. And then simply take their products over various things. But these are modules, so you have to make a sheaf out of that. So you take the constant sheaf on X closure by EX. So this is basically this construction I said in the beginning of the class. So beginning of the lecture. You make this, these are sometimes called skyscraper sheaves. So these skyscraper sheaves on X, exclosure, and exclosure is basically because our topology is pathological, our points may not always be closed sets. So you have to take the closure of that, and that will contain several points. And so you have to put basically on the closure, it is given by just these sections, and it's 0 outside the closure. That's why we call it constant. And sometimes it's called skyscraper. So you take the product of these, and one can easily show that F is embedded inside this, and this is a injective module. So that tells us that there are enough injectives, and so we can use this to define the cohomology of various functors. And that's what I'll do next time. In particular, you can also apply it to the constant. I mean, this is your sheaf of rings. ZX is my sheaf of rings. So I can use that. If I do that, then mod X by definition is just sheaf of abelian groups. So you can look at injectives in the sense of abelian sheaves of abelian groups, and there are enough of them also. So you can compute them in either this larger category mod X, or smaller category mod X if OX is a smaller sheaf of. Never mind. If OX is a sheaf of rings, and if OX is just this sheaf of rings, then in fact mod X is a much larger because it's like saying you're looking at all abelian groups. So you can also compute it using this, and anyway, it'll all turn out to be equivalent. So that's what I'll do next time. As my lectures go on, I'll be more and more sketchy, and I'll just give just the overall idea of what the duality formalism is. Okay, thank you.
So any quick questions? So thank you, Suresh. Maybe we'll take a 2-minute break and come back.
So I'll maybe switch off my screen or something like that, or stop sharing. Yeah, okay, thanks.